Hello, I am Karem Lozano Montero. I'm a doctoral researcher at the Laboratory for Future Electronics at Tampere University. You can visit our website and follow us on Twitter to know more about our research work. Today, I'm going to talk about our research topic, fully printed unobtrusive and skin-conformable piezoelectric energy harvester. The agenda of this presentation is the following. First, I will talk about wearable electronics and the main challenges when developing this type of devices. Secondly, I will summarize the main goals of this research. Then I will explain the fabrication process developed in this research work. In the results section, I will present the main findings of the sample characterization and of the energy harvesting experiments. Finally, I will present the overall summary of this research and possible future work. Introduction. Wearable devices are referred to small electronic devices which can be worn on the human body. The development of this type of devices have been growing tremendously year to year with a high interest in developing on-body flexible electronics. However, there are still some challenges when developing wearable electronics, such as flexibility, comfortability, and energy consumption. Especially, energy consumption plays an important role as the small size factor and portability of wearable electronics prevent the use of large and traditional batteries. Therefore, it is needed to develop new techniques to overcome these issues. Some alternatives are to minimize the power consumption, develop advanced battery techniques, and to study new energy harvesting methods. Objectives. In this study, we demonstrate a thin and fully printed flexible piezoelectric energy harvester. The fabricated device is based on an interdigitated electrodes structure, as can be seen in this figure. And the fabrication process is based on printing technologies using biocompatible polymers. Additionally, by decreasing its thickness, it can be skin conformable. The fabrication process of the flexible piezoelectric energy harvester is shown in this figure. A pyrolysis layer was deposited on a temporary glass carrier. Then the pyrolysis layer was UV sun treated for 15 minutes to improve its wettability. And an IDE structure was then inkjet printed using PEDOT PSS ink. This was followed by the deposition of the piezoelectric material VDF-TrFE using an automatic barcoder. Finally, the sample is peeled off from the glass carrier. The print quality of the samples was analyzed by measuring the dimensions of the IDE structure and the sensor thickness. Additionally, the piezoelectric properties of the sample were characterized. In this case, the polarization electric field loop and the remnant polarization were measured. The figure on the right side shows the experimental setup used to measure the energy harvesting performance of the fabricated sample. To perform these measurements, the sample was peeled off from the glass carrier. Then it was laminated to a PET foil, and the attached sample on the PET foil was then placed on a metal holder showed here. such that the harvester was facing downwards and the interdigitated electrodes were in parallel with the bending axis. The bending was induced from the top of the structure using a metal bar, and an oscillatory dynamic force was applied to the sensor using a piezometer. In this figure, we can see the fabricated sample after peeling it off from the glass carrier. In this table are summarized the main parameters of the sample characterization, such as the dimensions of the IDS structure and the electrical properties. The overall thickness of the device is approximately 21 micrometers, which allows skin conformability. In this graph, we can see the surface profile of the VDF-TrFE layer. The piezoelectric properties were also characterized. Here is shown a typical P loop measured from the fabricated sample. From this measurement, we can also get the remanent polarization, which was 6.4 microcoulombs per centimeter square for a coercive field of 61 volts per micrometer. The results of the energy harvesting experiments are shown now. And in this figure shows the frequency response of the flexible energy harvester without a resistive load. The maximum output voltage of 1.1 was observed at 60 Hertz, and this was selected as the frequency to characterize the output power of the device. Then the output voltage was measured as a function of an external load, and here is represented the measured output voltage and its corresponding current. The average output power was calculated using the previous measurements, and it was obtained a maximum value of 2.4 nanowatts. This corresponds to a power density of approximately 0.5 microwatts per cubic centimeter for a load of 100 mega ohms. The obtained power output is relatively small when compared to previously reported studies of piezoelectric energy harvesters based on VDF-TrFE. However, the process developed in this research introduces a novel and low-cost fabrication process when compared with previously reported studies where complex and expensive processes are used. Conclusions and future work. In conclusion, we have developed a two-step printing process of a flexible piezoelectric energy harvester. Its minimal thickness of 21 micrometers allows skin conformability. These results show the potential use of this type of devices for powering low power or energy autonomous wearable devices. Future work. In future, we are planning to develop an energy harvesting module where we will integrate the piezoelectric harvester with a diode bridge and an energy storage element. Additionally, we are planning to perform durability and reliability tests for our samples. And thank you for your attention.